shame. I really feel like the marketing person for the magnetic mirror was asleep at the wheel, and they lost out to cool names like tokamaks accelerators.
Greetings, Earthlings, and welcome back to Earthlings 2.0, the show where we imagine how we can be better versions of ourselves and build a collective future we actually want to live in. As we know, the world is facing an urgent challenge of both decarbonizing our energy mix as well as increasing how much energy we produce for the future. This is assuming AI solutions don't become more energy efficient and also assuming that we all continue to adopt EVs around the world. So we're facing this significant rise in energy demand. What are we going to do about that? Well, that's one reason why you might have heard a lot of talk about nuclear energy. And while existing nuclear fission technologies provide a stable source of low carbon energy, they do come with some significant challenges. Any of you who've watched the Netflix show Chernobyl know what some of those challenges might be. And if you haven't, go watch it. It's actually pretty good. So, long-lived radioactive waste. We still don't actually know what to do with it. In fact, if you listen to our To Nuclear or Not episode, I'll put the link in the show notes. That was episode 6. One of our guests admitted that it's all just in a warehouse somewhere, and we're just not going to do anything about it until we have a collective agreement, which is never going to happen. So it's just going to keep sitting in that warehouse. Anyway, catastrophic meltdowns, Chernobyl being an example, and the high cost of building and maintaining these reactors. At what point are we throwing good money after bad? So that's why small nuclear reactors, also known as SMRs, have also been getting some attention. They aim to address some of these issues like lower upfront costs eventually, faster deployments, and enhanced safety features once they're at scale. But they still produce nuclear waste. They rely on uranium fuel, which is associated with both mining and geopolitical risks, and they require regulatory approvals before widespread adoption. So that is to say, if they ever get out of the lab and into the pilot stage. In contrast, nuclear fusion offers a more sustainable alternative. You're not looking at any long-term radioactive waste. You're not looking at a risk of meltdown, and it's an abundant supply of fuel from hydrogen isotopes. So if we can scale fusion, it could fundamentally reshape the global energy landscape without all these trade-offs that fission-based solutions face. And so go ahead and click in the show notes for episode 27, which we called The Forever Fuel of Nuclear Fission. And that's going to give you a deep dive into how this technology works and its potential. So there's several nuclear fission startups attempting to bottle the sun and mimic our nearest star and how it generates energy. And our guest today is one of them. But before we get there, I'm your host, Lisa Ann Pinkerton. I'm the CEO of the award-winning technology PR firm Technica Communications and the founder of Women in Clean Tech and Sustainability. Before all of that, I was an award-winning reporter for NPR and PBS covering things from environmental science and healthcare to education and whatever else my editors asked me to do. Sometimes I just had to go cover the football game, which I didn't mind. And I want to thank all of you for joining us today, whether you're a new listener or a returning one. Thank you for being with us. We love bringing you these stories. It's our passion project. So thank you for listening to them and absorbing this information that we're providing. If you haven't already, we're going to ask you to do a few things to be more active within our community. Follow us on our social media channels, Earthlings Pod, and that's across all the feeds. You can go to our website for those exact links. We have a newsletter that we send out once a month, which is a digest of the episodes that are on the show. And if you're feeling financially generous, you can join our Patreon page where you will get early access to episodes as well as long interviews, because we only do 30, 45 minutes tops on these shows, but sometimes we talk for an hour and a half and it's really compelling. And I spend hours cutting it down. So go on over to Patreon. The link is in the show notes if you want to become a member. And thank you to Resource Labs for having us on the network. Today's tech spotlight is with Realta Fusion. They are developing a new approach to fusion energy that they say focuses on cost effectiveness, scalability, and sustainability. And our guest today is Kieran Furlong. He's the company's CEO, and he has over 25 years of experience as a fusion entrepreneur, a venture capitalist investor, and a chemical engineer. So he's built this deep understanding of the challenges and opportunities facing the fusion sector. So I want to welcome Kieran to the show. Welcome, Kieran.
Great. Thanks very much, Lisa. It's a pleasure to be here.
And I want to start by helping people separate in their mind these two concepts of how to generate nuclear energy, fission and fusion. Can you give us a high level primer?
Yeah, sure. So fusion is really around you start with very, very light elements and you're trying to fuse them together. So we're, adding atomic nuclei together, whereas fission is all about taking big, heavy atoms and splitting those and breaking them apart into slightly smaller atomic nuclei. So, they're both to do with, the material at the center of the atom, if you like, but they're coming at it from different ways. Fusion, you add light ones together, you build them up. That's actually the process that happens in the sun. So where we have fusion going on continuously, and that's what provides all of the energy that we have on Earth. So when you think about oil and gas, it's really just prehistoric sunlight that was being preserved. And then fission is at the other end of the process. It's large atoms which are then being broken apart and separated. So that's kind of the different mechanisms behind them. Fission, we've been doing it for a long time now. We've got power plants that have been running on it for decades. Fission, it's talk to the physicists around. It's easy, right? You just get a pile of hot rocks, you pile them up, and they get even hotter, and you run some steam and make some electricity. So that is the truth, right? It's actually pretty easy to get going to the point where that becomes one of the concerns around nuclear fission is the runaway reactions and the ability to control those reactions. And if you look at the other end of the periodic table, where we're bringing these lighter, smaller elements together and trying to fuse them, it's really difficult to do. So that's been the challenge why we have not yet mastered commercial fusion power plants, but we're working on it.
Well, we were able to figure out the other way, so I have a sense that we're going to figure out this one as well. And there's a few different approaches, and not to get too technical, but one is called magnetic confinement fusion, and the other is uh, inertial confinement fusion, I think is how you say that.
Yeah, so those are the two main buckets. There's a few in between. There's a few that combine those, but essentially, one way you can think about it is so the magnetic confined fusion. The sun has this huge. So with fusion, to get fusion to occur, you basically have something that we refer to as the triple product. But you've basically got to get your fuel hot enough and dense enough for long enough. The sun has got the huge advantage of density, right? It's just got this massive amount of mass, which is pulling in. So they've got extreme densities that we cannot come close to here on Earth. So we look at the other levers to get that same triple product, right? We can make things hotter, but we've got to try and find some way to confine it and keep it dense enough as well. Now, obviously, if we're going hotter than the temperature of the sun, there's not many vessels around or materials that we can construct a vessel of on Earth. So what we instead do is construct a bottle or a cage out of magnetic field lines. So essentially you create this magnetic cage to confine a plasma because the fuel that we have is in a plasma state. So some of your listeners, I'm sure, will be remembering, okay, solid, liquid, gas, and then there's that weird plasma one that goes beyond gas. That's where we've got charged particles. But because they're charged particles, they can be confined within a magnetic field. So a clever construction of a magnetic cage, you can hang on to a plasma and then heat it up and get it to the temperatures that we need for a fusion reaction to occur. So that's how magnetic confined fusion works. Inertial confined fusion is where you take a small piece of the fuel, right? So these hydrogen isotopes you mentioned at the opening, and you bombard them with energy from all sides at the same time, and you heat that little bubble of fuel up before it can expand. So that's where the inertia comes into it. And you essentially get all of the temperature of that small amount of fuel up very, very high, very, very quickly, and that's how you'll get fusion to occur there. But by definition, then you kind of got to keep doing that over and over again. In our particular approach with Realta Fusion, we've got something known as the magnetic mirror, and that's a magnetic confined fusion. But we're aiming for steady state operation of fusion for a fusion power plant.
Okay, and so you're doing the magnetic confinement version of fusion, and I've heard words like tokamak and stellarator for those applications. Are you using one of those designs, or do you have a different design?
No, we've a different design. So the technology, and it's a shame. I really feel like the marketing person for the magnetic mirror was asleep at the wheel, and they lost out to cool names like tokamaks and stellarators. But yes, our technology is something known as a magnetic mirror, and it's not, shiny metal reflecting. It's a mirror effect. So we essentially have these particles bouncing back and forth within the magnetic bottle that we've created. It was once the leading fusion concept in US based fusion research, and then lost a bit of ground to the tokamak back in the 70s and 80s. And when fusion funding was cut in this country back in the 80s, it was essentially put on the shelf, and the remaining trickle of funding was directed towards the tokamak. So things like mirrors, and so the magnetic mirror and the stellarators and so on, really had to take a back seat for a long time. And I think this is a really typical or a really important point to get across to your listeners. I'm sure some of them, if they're have been looking or reading up about fusion, will have come across the old chestnut of, oh yeah, fusion is the energy of the future and always will be, or it's 30 years in the future. I always tell people, listen, that's just one of the variables. It's time multiplied by dollars. And there
Yep.
was this dearth of funding for a number of decades on fusion, but private capital is now flowing into fusion funding. Governments are taking a look at it again as well, and we've seen this real upsurge in funding for fusion, which is accelerating the progress. And that funding is coming in because we are coming around the corner on some key enabling technologies as well.
It's funny that you mentioned the finance piece because I was thinking in preparation for this interview about the fusion development. And I was thinking, well, would we even be here with the nuclear reactors that we have had there not been a war and, and the Manhattan Project to create the atomic bomb? Not that we need a war to funnel money into fusion, but I feel like the fission side of the industry kind of benefited from that massive influx of both political will and capital to help boost its exposure as an industry.
Yes, for sure. And I think, look, personally, I'd love to believe that the climate emergency is why a lot of this capital is flowing in. To some extent, that has brought new investors to look at novel forms of energy generation. But I think the real reason is we just need more energy. We will always need more energy, and we've got a voracious appetite for it as humanity. And definitely, I'm glad that's part of the equation. So I grew up in Ireland. Was relatively poor country by European standards when I was born. Now it's one of the wealthier ones, but it's 5 million people, give or take, right? So it's like that's not a huge thumb on the scales of the Earth's sustainability balance. But if we try to give the same quality of living that we enjoy in the US to 10 billion people that we'll have on the Earth by 2050, or even if it's 9 billion, we really only have about 2 billion which are enjoying the kind of lifestyle that we need. And I feel like that's a big topic to tackle. That's kind of what I've been focused on for much of my career, but trying to do so in a sustainable manner. And we see these things every now and again. Right now, there's lots of discussion around AI, right, and data centers. A few years ago, it was a big surprise that Bitcoin mining was consuming so much electricity. We're going to find new uses for energy. We just need more of it. But energy is what underpins everything in our economy. So if we want people to have food, clean water, shelter, clothing, mobility, or funny cat videos on YouTube, all of that depends on energy. And I think, investors are seeing that. They see the need for more forms of energy. We definitely need an all of the above approach. And energy transitions take time as well, right? There are still parts of the world where, burning dried out cow dung, for example, is a fuel, right? So it's
Hmm.
like biomass is still there. So it takes a while for these transitions to take place. And ultimately, hopefully, as humanity will come to sources of energy which are the most economically feasible, the safest, and the least destructive to the environment. And we'll see what that turns out to be. But I think fusion has it's got a strong probability of being that desired form of energy for the future of humanity.
Yeah, given it a long enough timeline, enough money, we'll figure this out, right? It just depends on the two combinations coming together. So let's go back to your magnetic mirror fusion concept. Describe for us what it looks like. And we're going to put a picture in the show notes and on the video here. But for those of us who are listening, what does this device look like right now?
Yeah, so first of all, it's a cylinder. So you talked earlier about tokamaks and stellarators. Tokamaks are often described as donuts, right? So they've got this toroidal shape. And then a stellarator is that funny, twisty French donut in a circle, right? So it's a twisted donut. Ours is a very straightforward long john, right? It's just a straight cylinder. So that's the first thing. As a chemical engineer, when I saw it, I was like, hey, that makes sense to me. I can imagine how that gets machined. I can imagine how it gets manufactured, how it gets maintained, and how we wrap a heat exchanger around it to take all that energy from the neutrons that are produced in the fusion reaction. So first of all, it's a cylinder. In its simplest configuration, which of course is referred to as a simple mirror, we have two big magnets on either end of that cylinder. So these are very high field, very strong magnets, which that's one of the unlocks that's enabling us to revisit this technology is the latest generation high temperature superconducting magnets enable us to get to very, very, very high magnetic fields. In fact, we spun Realta Fusion out of an experiment at the University of Wisconsin in Madison, experiment known as WHAM, where we started it up last summer, and it was a world record breaking experiment. So the strongest magnetic field ever applied to a fusion plasma at 17 Tesla. So, really, really strong magnets. We've got two of those on either end of this cylindrical pipe-shaped vessel, and that's our vacuum vessel that will contain the fusion plasma.
Okay, and then so once you've got this set up, how does it work?
So you have it set up. Essentially, what you end up with the big high field magnets will kind of be pinch points on either end of what would otherwise be cylindrical magnetic field lines. So you end up with something that looks like a candy wrapper, like a Tootsie Roll, where you've got the cylinder in the middle, pinch points, and then it kind of flares out on either end. Within that cylindrical part in the center, the plasma, the charged particles of the plasma will rotate, gyrate around the magnetic field lines, and they kind of travel along the magnetic field lines towards one of the big magnets. They get closer and closer, and they begin to spin faster, but they stop moving forward. They hit a bounce point, and then they flip back and start going in the other direction. And they're doing this at millions of meters per second. So essentially, you've got your magnetic field lines in that Tootsie Roll shape. You've charged particles, and they're bouncing back and forth at extremely high speeds between those two big ring-shaped magnets. And if we do that for enough times, at high enough energies, eventually some of those particles will begin to collide, and that's when the fusion will occur. If they collide at just in the right conditions, so the hydrogen isotopes you mentioned earlier, we're talking now about deuterium, which is heavy water, and tritium, even heavier water. When they collide, DT fusion, we will form a helium ion. So helium is your byproduct, but you're releasing a neutron from that, and it's one of those where you've basically got 2 plus 3 doesn't quite equal 5. A small bit of the mass gets converted into a massive amount of energy.
I like how that was a simple explanation, and like I said, there's a link of a video that they have on their website in the show notes. I encourage all of you to go watch that video. It's short. It's going to give you a visual on what Kieran just explained. Now, Kieran, how big is this cylinder?
Yeah, so first of all, you'll see some pictures on our website as well of the WHAM experiment at the University of Wisconsin. That I would say is maybe 6 to 8 meters long. The vacuum vessel in the middle is about a meter or so long, and the magnets around that, if you were to lay them on their site, but they'd be a normal sized coffee table, right? So it's actually pretty compact. Now, we want to scale that up so we can get to a full scale commercial energy producing plant. We'll go a little larger, but you'd have something where the cylinder might be, 2 meters in diameter or so. And then around every 10 meters would be around 50 megawatts of power output. So, you're getting to something that you're not going to put one of these in your backyard or in your garage, but you could definitely see one being like a campus cogen facility or, a power plant on a large industrial site next to a data center, or we could put a few of these together for grid scale power plants.
So it sounds like they can be modular and you can build up a plant to the size that is needed for whatever energy is required for that site.
Yeah, absolutely. That's one of the key advantages of our technology is this modular nature. So one of the challenges you mentioned nuclear fission, for example, at the start. One of the challenges with that in terms of the cost, I think engineers have tried to address human emotions like fear with extra engineering safeguards, and thus they've pushed the cost up. But also, those things are very large machines that are stick built. You kind of build one, you design one, build one. What we're looking to do, which is similar to some of the SMR type technologies, is to be able to have something which you can have replicable modules that you would manufacture in a centralized location. You come down the learning cost very quickly then by making the same thing over and over again, and then going out to the energy customer who needs that. We effectively would say, well, how many modules do you need to get to your desired power output? So again, we get the advantages of making the same thing over and over. So we get good at it and we get cheap at it. And then we get to go and basically say, well, how many units do you want? Do you need 150 megawatts, 300 megawatts, 500 megawatts? What's the application that we are looking to fulfill?
So you talked about the demonstration that you did at the University of Wisconsin. Where are you now in your development?
Yes, so we have an operating fusion experiment. So I think that's something that not every fusion company, in fact, very few fusion companies can say. And that's a benefit of our close partnership with the University of Wisconsin. We now are a team of 16 people. So we just had our latest scientist join us last week. So we're small, but growing. And we're leveraging lots of external expertise as well by working with the University of Wisconsin and some of the national labs. So we have our, if you want to think of that as your benchtop scale, although as I described, it's a bit bigger than that, but we've got experiments. We're running those experiments. We're figuring out how to steer the plasma, how to stabilize it, how to get a handle on the plasma. And this is one of these amusing things. As I said, I'm an engineer. I like to think of things in well, how many days have we kept that running, or can we get to, kind of run for 12 months before we need a shutdown? The physicists are looking at what's happening in the plasma, and for them, milliseconds is an eternity because of the speed of these particles moving around. So you can see a lot, even in very short experimental bursts, which is kind of how we're doing it right now, which is more a limitation of the equipment. But we'll run short 20 millisecond bursts and see what happens to the plasma in those experiments. The next step for us is to build up to our next device, what we call Anvil, which will be set in the Realta Forge. And Anvil will essentially be a supersized version of the WHAM experiment, where we get to the right kind of size that we would need for a commercial plasma. And we also get to move away from some of the, kind of hassle factor of dealing with something at a smaller lab scale. So that's the next step for us. We'd aim to have that operational within this decade. And then that will essentially allow us to de-risk the remaining technology, de-risk the technology to the point where by the mid-2030s, we would have a commercial fusion plant operating.
Okay, so what are some of the challenges right now that either you're facing with your development or that in general fusion is facing with its development, besides the finance piece, which we've talked about?
So we get asked about these kind of things. Everyone always wants to talk about, the high temperature superconductors. Can you get to the magnetic field strengths? Will there be enough tape made in the world? Those are all very engineering kind of concerns. I've got absolute confidence that if we put enough brain power to work on this, we're not trying to defy any laws of physics. We're merely trying to do something that's really, really hard, but humanity has shown it can do really hard things before. We just need to get the right brains on it. And then that's one of the challenges I see is, can we get enough people to come work on fusion? Can we get enough people, studying the right topics in high school and in university to then come and be our physicists and material scientists and so on that we need? So that's a challenge one. Particularly, there's a massive amount of work in fusion research is around simulation. So high, kind of massive parallel computing and running these really, really complex models. Um, those are the kind of people and skill sets that are, being pulled towards things like AI. And a good friend of mine is doing an AI startup company, but I'm always lamenting, like, why are all these brains going off to figure out how to make it easier for us to order our pizza, right? Doesn't seem to be the best use of brain power. So one is, can we get enough brain power to fusion?
Yeah, I agree with what you're saying because if you think about it, it's about so like the nuclear fission industry. I mean, it's, we're talking about radioactive waste. We're talking about meltdowns and things that are really scary. So I can understand why young folks might not be inspired to build a career around that type of technology and why they might be attracted to things like AI. But here you are with fusion technology saying that those risks aren't a part of the equation, and so there is more of an aspirational aspect to it that I think people would be attracted to. But that does raise one of my other questions for you, which is, well, what could go wrong in one of these fusion reactors, and what might happen?
Right, right. Yes. So what could go wrong? Well, first of all, we should talk about the waste side of things as well. So we don't use any, kind of fuel like uranium fuel rods and something. We don't end up with spent fuel rods that have to be, surrounded in concrete and buried or dropped in a pool for 100 years to cool off and then buried in the bottom of a mountain in Nevada. But we do have equipment that's being exposed to neutrons. So at the end of life of that equipment, it can be radioactive. Now, by careful selection of the material, the careful choices, we will hopefully be able to design plants in a way that keeps that to a minimum, to the point where it's kind of something similar in terms of handling as a X-ray laboratory that you're tearing out of a hospital, for example. So that's just to make sure that we're not we want to be clear with people that, yeah, there's some things that we have to figure out as well when it comes to the waste product, but it's the material that's used to construct the vessels. In terms of materials being able to run away, we're dealing with a very small amount of mass. So going back again to this, can we get something hot enough, dense enough for long enough? To do that, we actually end up dealing with a very small piece of mass. If the plasma gets out of control and it touches the side of the vacuum vessel, the magnetic cage essentially breaks in some way and it bubbles out and touches it, yeah, you might cause significant damage to the inside of that vessel, but that's about it. It's not going much further. So you don't have enough stored up energy in the plasma when you compare it to the fuel rods in a nuclear fission plant, for example. There's stored energy in the magnets that we're using, so we have to be very careful and cautious about how we operate and work around these very big, powerful magnets as well. So there are things that, again, good, proper practice and procedures can take care of those things. Um, in terms of what can go wrong, yeah. So like, there's not this worry about something going boom, right? It's they're like, we're not dealing with that. That's been the real challenge with fusion, is not just how you can get it to go boom, but how you can get it to just be like a lit match and keep going for a period of time. Before we were talking about the pile of hot rocks for fission and so on. One analogy perhaps is, it's like you take a basketball, you push it down a hill, it rolls down a hill and gets faster and faster. That's fission. For fusion, you're trying to spin that basketball on the end of your finger for
And you have
days at a
to,
time, right? So it's it's a lot more difficult, and it takes active control, right? So you're actively trying to control, hang on to, and steer that plasma into the conditions that will make fusion happen.
so let's sort of zoom out a bit. You're working on getting to that next stage of development, that commercial size. Other startups, it sounds like, are working on trying just getting to their first pilot, whereas you've moved beyond that with your WAM experiment. So, what is the timeline you think, given what's going on right now, what's the timeline for fusion in terms of when we might see a commercial installation from you or anybody else?
Yeah, as I think I'm going to be specific here and talk about commercial fusion energy, right? So actually, a power plant or producing heat for an industrial process. I'll put that as mid 2030s. That's definitely when we plan on having our first commercial plant. There are some companies, some startup companies who are a bit more ambitious and aiming to get something by the end of this decade. I wish them all the best of luck. We're going to see what happens, but I think we're within that kind of 10-year time frame from commercial fusion energy. As regards to commercial fusion, if I was to stop it right there, as your question was, there's people already doing that. So here we're based in Wisconsin, and not too far from us, there's a company called Shine who are figuring out, okay, we can make fusion neutrons. It would not yet be net energy producing, but the neutrons themselves can be very useful. And they're looking at business applications like medical isotope production, neutron imaging, radiation hardening, and so on as well. So there are other things you can do with fusion. We're focused on the kind of the big kahuna. We want to make zero carbon abundant fusion energy.
So fusion is already happening now, but on a much smaller scale and perhaps very specific applications. And so it's not pie in the sky in terms of any commercial activities happening in the future. Some stuff is already happening right now, and then the bigger applications you're saying are coming in the mid 2030s or sooner, assuming some of these companies can make good on their ambitions.
Yes, absolutely. Yes. So I'm not sure if I mentioned the name of the company, but Shine is the company here in Wisconsin that's doing some of those things already. So yeah, there's a spectrum of things you can do with fusion. But the big win and why the investors are really kind of flocking to the space and paying attention is the promise it holds for energy. And yeah, we've got things like, yes, the current AI boom is directing everyone's attention to energy once again. I've been working in this, like you said, for 25 years and more. And it's funny, like the wheel comes around, all of a sudden people pop their head like, oh, energy is really important. And you're kind of like, yeah, it never went away. It was always really important, always will be. It's what everything else, requires. But I'm glad you're paying attention for this year.
I have a friend of mine, Neil Dykman, who's a venture capitalist, and his favorite line is energy is life, everything else is details.
Right. I concur. Yes.
Yeah. Well, thank you so much, Kieran, for being on the show and taking us through this side mission of fusion. And we're gonna keep tabs on you and appreciate getting the updates from you as things progress.
Great. No, glad to have the opportunity to come on board here. And like I said, I think just getting more people enthusiastic about fusion or at least aware about fusion is a really important part of our development. So thank you for the opportunity. Appreciate it.
Oh yeah, you're welcome. That's our aim here. And Earthlings, thank you as well for joining us. And we'll see you again on another turn of this beautiful blue-green space flower that we call home.